Hello everyone and welcome to another Plaxis 2D tutorial. In this tutorial, I'll be showing you how to do a NATM model in Plaxis 2D. So in short, for those that do not know what NATM stands for, NATM stands for the New Austrian Tunneling Method. So it's mainly used for mountainous areas where any tunneling is required. And excavation is usually done by inserting explosives into drill holes, and once the debris is removed, shotcreting or rock anchors installed, and occasionally you might have other stabilizing methods employed. So if you want to know more about NATM construction methods, you can go to the description box. I have linked to additional videos that you can refer to. So for this video, I have opened up the Plaxis 2D tutorial over here. So we are in chapter 7, excavation of an NATM tunnel, and the main objectives are to model the construction of an NATM tunnel using the deconfinement method and using gravity loading to generate initial stresses. And this diagram here is a pretty bad representation of what the model should look like. As we progress through this exercise, you'll see the larger scale screenshot of this small drawing over here. So first, let's create the new project. So I will name this as NATM tunnel tutorial. And moving on to the model tab over here, you can see that we are supposed to use a plane strain model over here, and the element should be set to 15 noded over here. And we've already done so. We've already chosen plane strain and elements are set to 15 noded here. Now moving on to X minimum and X max and Y min and Y max values. So for the X minimum value, we are using a minus 50.0 meter value here. And for the X maximum value, we are using a 50.0 meter value here. And for the Y minimum value, we are using a 0.0 meter value. And for the Y maximum value, we are using a 35 meter value over here. So moving on to the constants tab over here, you can change the unit weight of water to 9.81 if you want. And under the Cloud Services tab, there's nothing to change over here, so we can just click on OK. So we quickly scroll down in the tutorial over here. We can see that there are 3 different boreholes in this one model. So one borehole is set at minus 22 meters here for X. And the second one is set to X equals to minus 14 meters over here. And the final borehole is set to X equals to minus 7.0 meters over here. So let us put in all the boreholes in this model over here. So click on this Create Borehole tool. And we'll place one at minus 22. Just click on OK. Minus 14. And lastly, minus 7. And in this Modify Soil Layers tab over here, we can actually display all 3 of these boreholes over here. We can do that by clicking on the boreholes button over here. And under the select option, you can see borehole 1, 2, and 3. Each at minus 22, minus 14, and minus 7 meters respectively. So if you select them one by one, you can see all the boreholes in this model that are selected in the select option over here. So this is an efficient way of dealing with multiple borehole logs in one file. And as we can see in this diagram over here, there are 3 different soil layers, and I will import the material shortly. So first we need to set the heights of the layers. So for this first borehole, we have 24 and 24 for the first layer. And for the second layer, it's set to 11. And the final one is set to 0, as you can see. And in the second borehole over here, you can see that the first layer starts at 30 and has a bottom of 30, meaning it has 0 thickness. And the second layer is set to 11 over here. And the final layer is set to 0. And for the last borehole over here, you can see the top is starting at 35 meters for the first layer. And it ends at 30 meters for the bottom of the first layer over here. So key in 35 and 30 over here. And the rest are the same for layers 2 and 3. So just key in 11 and 0. And that's it. So for the materials, I'll just click on this materials button here and I will go and import the materials that I've already created for this exercise. So we have 3 materials. As you can see, there's a top layer, clay siltstone and clay limestone. And I'll go through each one of the properties for each of the materials. So back to the material import. So I've already found all 3 of the soil materials / rock materials that I've already created beforehand. So I'll click on this arrow over here. So I've already imported all 3. So let's start from the top layer over here. So if I double click on the top layer, you can see that for the general tab, we need to use a hardening soil material model for the top layer, and the behavior should be drained. And these are already set correctly already. And for the unsaturated and saturated unit weights, they are 20 and 22 kilonewton per cubic meter respectively. And for the initial void ratio, it's set to 0.5 over here. Now moving on to the parameters tab over here, you can see that the various stiffnesses are defined over here. And for the first value over here, the second stiffness in standard drain triaxial test, or also known as E50 ref, it is set to 40,000. And it's already set correctly here. And the tangent stiffness for primary odometer loading, or E odometer ref, is also set to 40,000 over here. And the unloading and reloading stiffness, EUR ref, is set to 120,000 over here. So as you can see over here, we've already set all the stiffnesses correctly. And the power value is set to 0.5, which is set correctly here already. And moving on to the cohesion and friction angles. So the cohesion value is set to 10 kilopascals here, and the friction angle is set to 30 degrees. And one thing that I forgot to mention is the Poisson's ratio, mu UR over here. You can find it over here in the advanced section here. So it's already kept at 0.2, which is correct. Now moving on to groundwater, there's nothing here mentioned other than interfaces. So nothing in thermals as well. And now that we are in the interfaces tab, we need to look at the tutorial. So it says that the interface strength should be rigid and the R inter value should be 1.0 for top layer. So we've already made sure that the strength is rigid and the R inter value is 1.0. And there's nothing left to change in the initial tab over here, so we can just click on OK. So looking into the clay siltstone material over here, we can double click on it over here. And it says that we should use the Hoek-Brown material model and we should use a drain behavior. We've already done that over here. And the unsaturated and saturated unit weights are set to 25 kilonewton per cubic meter. Initial void ratio is at 0.5. Now let's move on to the parameters tab here. So this is where it's slightly different, or should I say very different from the typical Moore Coulomb or hardening soil model parameters here. So as you can see, we have the Young's modulus set to 1 million, Poisson's ratio set to 0.25, and you can see that it's already set correctly here, 1 million and 0.25 for Young's modulus and Poisson ratio respectively. And moving on to the Hoek-Brown parameters here, you can see the uniaxial compressive strength over here. It's set to 25,000, which is already set correctly. And the material constant for intact rock is set to 4.0, which is set correctly as well. The geological strength index is set to 40 and the disturbance factor is set to 0.2. So these two are already set correctly already. And the latency parameters here, we can see there's a 30 here and a 400 here. And we've already keyed in those values here. So we can just scroll through groundwater. There's nothing to change over here. And there's nothing to change for thermal here. Now in the interfaces tab, we need to be very careful here because it seems that the interface strength is set to manual over here. So it's already set to manual correctly and the R inter value is 0.5. So there's nothing left to change here. So moving on to the initial tab, there's also nothing left to change here. And we can just click on OK. And now finally, we can look into the clay limestone material. So double clicking on it, we can see the general tab here. And it says that the clay limestone will have a Hoek-Brown material model, a drain behavior, unit weights that are set to 24, and an initial void ratio of 0.5. So we've already set the material model to Hoek-Brown. The drainage type is set to drain. Unsaturated and saturated unit weights are the same at 24 kilonewton per cubic meter. And initial void ratio is set to 0.5. So moving on to the parameters tab here, the Young's modulus of the clay limestone is set to 2.5 million with a Poisson's ratio of 0.25. So these two are set correctly already. Moving on to the Hoek-Brown parameters of the clay limestone, we can see the uniaxial compressive strength is set to 50,000, which is set correctly here. And the material constant for intact rock is set to 10. And the geological strength index is set to 55. And the disturbance index is set to 0.0. And finally, for the latency parameters, it is set to 35 degrees and 1000 kilopascals respectively. So there's nothing to change in groundwaters over here and nothing to change in thermal. And for interfaces, we need to check once again. So for interface strength, we need to keep it at rigid and the strength reduction factor is set to 1.0. So these are already set correctly over here in this tab. And there's nothing left to change in the initial tab here, so we can just click on OK. Click on OK. And if we look at the diagram above over here, the first layer is the top layer, as the name suggests. The second layer would be the clay silt over here. So clay silt stone. And the final layer at the bottom would be clay limestone. There we go. So we can just click on OK. So hit escape twice to get rid of the create borehole tool. And let's move on to the structures tab over here. So this is where it's very important for us because this is where we are defining the tunnel itself. So if we scroll down, we need to define the tunnel using the create tunnel button here. And it says that we should place the tunnel at 0.0, 16.0. So find 0 meters here and move up by 16. So this is the correct spot. left click once, and the Tunnel Designer tab will pop up. So now we have quite a few things to do. There are many steps here, so I'll go through each one. So the default shape option should be free. So it's already set correctly to free here. And we need to go to the Segments tab right now. And once we are in the Segments tab, we need to create 3 different segments. So the first segment will have a radius of 10.4 meters and an angle of 22 degrees for the segment angle over here. And we must change the segment type to arc. So I'll click on this add button here. I will change the segment type to arc, and radius will be 10.4 meters, and segment angle will be set to 22 degrees. And let's add another segment over here. So just click on this add button again. Make sure that the segment type is arc. And if we look back over here, the radius is set to 2.4 meters here. And the segment angle was set to 47 degrees. And the final segment here will have a radius of 5.8 meters and a segment angle of 50 degrees. So I'll quickly change to arc. And we have a radius of 5.8 and a segment angle of 50. So it says over here we should extend to symmetry axis to complete the right half of the tunnel. So we just need to click on this button here called extend to symmetry axis. And now all we need to do is mirror this part over here to this side over here, so that we can have a complete tunnel. To do this, we just need to use the symmetric close button. So left click on this symmetric close button over here, and there you go, we have our tunnel defined already. So it's quick and easy. So before we click on the generate and close for the tunnel designer, we first need to create this subsection over here. We need to create this part over here of the tunnel. So this is done by going to the subsections tab, and it says that we need to add one subsection over here. So offset 2 will be set to 3 meters over here. So you can find offset number 2 over here at the left over here. So type in 3, and segment type should be arc. And the set radius should be 11 meters over here. So I'll type in 11. And the segment angle should be set to 360 degrees. As you can see, if we change it from 90 to 360, we have a full circle over here. Next, we must select the entire region. So to do this, we can just click on this selection tool over here. Select everything. And what we want is to only get this part over here. And to do this, we can just click on the intersect button. And all we need to do is select on this select tool over here to select this part of the circle. Hit delete. And now we have the correct shape over here already. So now we have the correct shape for our tunnel. As you can see here, if you scroll down, this is the correct shape of the tunnel. But there are a few things missing in our tunnel here. We have not defined a material for our tunnel, and we have not defined an interface for our tunnel as well, both of which are very important. So in order to define a material for our tunnel, we need to first go to the properties tab here. We need to use the select multiple objects tool over here. Select everything, right click, go to create, and you can create a plate over here. And we have not assigned a material, so we can use the shortcut Control M And we can go to plates over here, and I'll create a new material. So I'll name this as the tunnel lining. And the material type will be set to elastic and isotropic. So we've already set it to elastic and isotropic. So if we set it to isotropic, the axial stiffness will be the same in two directions over here. So the axial stiffness will be set to 6 million kilonewton per meter. And the bending stiffness will be set to 20,000 over here. And the weight is set to 5. And finally, Poisson's ratio is set to 0.15. And prevent punching is left as unticked. So we can click on OK. And click on OK. And now we can assign the material for our tunnel first. So we have tunnel lining over here, and we can assign it to this tunnel. And it says clearly that we must use a negative interface for our tunnel. But one thing that we need to note is that this excavation level should not have an interface over here. So we need to just click on the select tool, select elsewhere, and let us select the outer parts of this tunnel. We can do that by holding shift and left clicking and dragging. So I've already selected the outer shell of the tunnel, so I can just right click and go to create and create negative interface here. So now that we've already created our tunnel, and we've already given it a material, and we've already created a negative interface here, we can go ahead and click on the generate button, and we can click on close. So there we have it, our tunnel with an interface here. So we can scroll down and we can see that we need to generate the mesh now. So go to mesh, and it says that we must use a medium option over here. It shouldn't take long to create. So it's already created over here. And we can view the mesh by using the view mesh button over here. So I'll just click on agree and continue. So as you can see, the mesh over here in this screenshot is very similar to the mesh that we have in the output tab over here. And if we scroll down, there are some things to note about the calculations. We must use a plastic analysis and stage construction. And we are taking into account 3-dimensional arcing. And this is emulated by using the beta method. You can read up more on this short paragraph on your own. So for the initial phase, we can quickly close this output tab here and move straight to the stage construction phase. And it says that we will be using the gravity loading method for the initial phase. This is because the soil layers are not horizontal, in the sense that we have some slope soil over here. So double click on this initial phase and you can see calculation type here. So we're changing it to gravity loading. And remember to use stage construction over here, and we can keep the pore pressure at phreatic if you read ahead. And as you can see, the water will not be considered in this example. The general phreatic level should remain at the model base. And make sure the tunnel is inactive in this phase. So if we click on OK, we can see that the whole tunnel is not active. So moving on to the first phase of the tunnel excavation. So we can add one phase here, and let's use the toggle activation tool, and we need to deactivate this soil over here. And as you can see, it states that the deactivated cluster is still selected. In the selection explorer, set the confinement to 60%. So what this means is that if I select on this excavated soil over here, we should set the deconfinement to 60%. So now in the second phase, we see that we need to activate this temporary lining over here. So back to the toggle activation tool, we can select all the points that are of interest. And that's it for this face over here. And we need to set the deconfinement to 100%. So change this back to 100% here. And for phase 3, we need to deactivate the temporary partition over here. So add another phase, and we need to deactivate this partition here in the middle, and we need to deactivate the soil here. And what's different is that this top part here will be set to a deconfinement of 100%, and this part here will be having a deconfinement of 60%. So type in 60% here. And moving on to the fourth phase, which is the final phase, we can add another phase here. And using the toggle activation tool, we can activate the remaining parts of the tunnel over here. And this bottom part here can be set to a deconfinement of 100%, as you can see over here. And before the calculation, we need to select some points for curves. Essentially, this is useful for us if we plan to plot graphs. So I'll just select a point somewhere up here and somewhere down here, and click on update. Do note that the selected points don't really matter that much in terms of location. It doesn't affect the calculation. So click on the calculate button, and it should calculate this whole project pretty fast. So it's already done. So now let's view our results over here. Click on I agree and click on continue. So in results over here, we can see that we are using this tool over here. So just click on this tool, which is called drag a window, to select structures. So left click and drag, and we need to select the plate. Click on view, and then we can view the bending moment easily just by going to the forces drop down here and click on bending moment, and you can see the bending moments here. And there you go. This is the shape of the bending moment diagram as shown in the tutorial. And this is the bending moment diagram as shown in our attempt to recreate the tutorial's results. So as you can see, the shapes are very similar. So we've already done a very good job in mimicking most of the bending moments features over here. You can see this peak over here and over here, and peaks over here, and over here, as shown. Although we are missing some parts here and here, but nonetheless we have already managed to mimic the parts here and here as well. And that's it for this video today, folks. I hope that you found this video useful. And if you want to watch more Revit tutorials or civil engineering related softwares, do consider subscribing to my channel because it's free. As always, stay safe in these unprecedented times. Take care, keep learning, and goodbye.